Today we're going to be practicing how to graph rational functions once more, taking on the function of f of x is equal to x minus 3 times x minus 1 divided by x plus 2 times x minus 1. We must first determine whether this function have any holes. In this specific example, it does. It will have a hole when x is equal to 1. I know this because I can redefine f of x to be equal to x minus 3 divided by x plus 2, which in this redefined function will have a value for when x is equal to 1. It will not have a value for x equals to 1 in our original function, because when x is equal to 1 in our original function, the denominator will be 0, and hence making the ratio incorrect, because the denominator can never be 0. So our hole will be 1 comma, substitute 1 into the x variable to get negative 2 over 3. That will be our hole coordinate. Next, we must find the vertical asymptote, if it has any, for this function. The vertical asymptote we can simply find by substituting variables of x that will make the denominator 0. In this case, both x is equal to negative 2 and x is equal to positive 1 will make the denominator 0 in our original function. But once again, we have found another way to rewrite f of x so that x will be defined when x is equal to 1. Therefore, for our f of x in this specific example, it will not have two asymptotes, vertical asymptotes, but it will only have one vertical asymptote, that being x is equal to negative 2, because when x is equal to 1, it will be defined within f of x, because we can rearrange f of x to get x minus 3 divided by x plus 2, where when x is equal to 1, we'll have some value. In this case, negative 2 over 3. Moving on to our horizontal asymptote. Our horizontal asymptote we can simply find by taking the ratio of the coefficient of the largest power in the numerator divided by the coefficient of the largest power in the denominator. That will be y is equal to 1, because the denominator's coefficient for the largest power will be 1, with x squared's coefficient, and the numerator's coefficient for the largest power will also be 1, with x squared. Moving on to our oblique asymptotes, if it has any. Since we already have a vertical asymptote and a horizontal asymptote, it will not have a oblique asymptote. So we can safely say there isn't any oblique asymptotes in this function. Then we must find the x-intercepts and the y-intercepts. We can find the x-intercept by simply substituting 0 for f of x. So when x minus 3, or rather not x minus 3, when x, that's 0. So the x-intercept should be 3 comma 0. And that's it. And the reason why it's 3 comma 0 is because we find the x-intercept by simply finding what value of x will result the numerator to be 0. In this case, once again, likewise to our vertical asymptotes, we have two variables, substitutions of x that will make numerator 0, that being x is equal to 3 and x is equal to 1. But we only take x is equal to 3 for our x-intercept because, once again, there is a defined point when x is equal to 1 that isn't an x-intercept. When x is equal to 1, it will be 1 comma negative 2 over 3. Therefore, we only have one x-intercept being 3 comma 0, 3 being the value that will make the numerator 0. Then we move on to our final attribute, the y-intercept. The y-intercept we can simply find by substituting 0 for the x variable. In whatever quantity that comes out to will be 0 comma that certain quantity. So 0 minus 3 will be negative 3 times 0 minus 1, that will be negative 1. 0 plus 2 will be 2 times 0 minus 1, that will be negative 1. We can divide negative 1 and negative 1 and cross them out to get the coordinate being 0 comma negative 3 over 2. That will be our y-intercept for this function. And now we can start to graph it. We can first draw out our vertical and horizontal asymptotes, which I'll be doing in this red color for x is equal to negative 2 and y is equal to positive 1, which will be right here. Now that we have our asymptotes drawn out, we can plot the y-intercept. The y-intercept is 0 comma negative 3 over 2 or 0 comma negative 1.5. So that will be this point right here. Furthermore, we also know the x-intercept. The x-intercept will be 3 comma 0. And now we can begin to sketch. You can see here that this function in this bottom right hand corner must pass through these two specific points while not crossing the two vertical and horizontal asymptotes. So it will look like this. It'll come up from negative infinity, cross the 2 points, and bounce up and infinitely try to hit y is equal to 1. We can be sure this is true by substituting certain variables for x to find out whether it goes to positive infinity or negative infinity. When x approaches negative 2 from the right hand side, say x is equal to 1.99, we can substitute that into our function. 1.99 minus 3 will be a negative value times 1.99 minus 1, a positive value, or result in a overall positive, or rather negative value in our numerator. 1.99 plus 2 will be positive, 1.99 minus 1 will be positive again. So our final outcome in the denominator will be another positive value. A negative value divided by a positive value will result in another negative value. Therefore, when x approaches 2, or negative 2 rather, from the right hand side, it will go down to negative infinity, whereas when it approaches infinitely goes out rightwards. So like it infinitely goes to the right. You can substitute any variable that's to the right of our x-intercept, 3, 0, it will always be positive. Say 6, for example. Let's put x equal to 6 to find out whether this is true or not. 6 minus 3 will be 3. 6 minus 1 will be 5. 6 times 5 will be 30. That will be a positive quantity. 6 plus 2 will be positive. 6 minus 1 will also be positive. A positive divided by another positive will result in another positive value. Hence, when x is going to positive infinity in the x direction, it will go towards y is equal to 1, our horizontal asymptote. And then, if it's not already clear, we can sketch out the other half of our function like this, because it can never touch the asymptotes, and it must be between this region right here, because we only have these two specific points on the x-intercept. This left hand function, upper left function, graph rather, cannot touch the x-axis at all, because we only have one x-intercept, that is 3, 0. Neither can it touch the y-axis, because it doesn't have another y-intercept. The only y-intercept we have is negative 1.5, 0, negative 1.5. Therefore, our function must be right there as so. And here we have graphed out our second example of another rational function.